All right, so what we're going to do to finish up 10.5 is we're going to rationalize denominators. And we're actually only going to work with monomial denominators and only square roots. So whenever you see the directions rationalize, it's probably not a word you run into before in math. So I find people, they see rationalize, they don't know what to do, because these problems look like some others that we've done. So first we're going to talk about what is the purpose of rationalizing a denominator. And it's really, what's our goal when we rationalize? And it's, there should be no radicals in the denominator. So when we're done rationalizing, when our directions say rationalize, our whole goal is that there are no radicals left in the denominator. And for square roots, that's a pretty easy task. Now, sometimes there's a shorter way to do this, but we talked about last time, if I had the square root of 5 times the square root of 5, what did I get? Square root of 5 times the square root of 5. Multiplying. You got to multiply the radicands. Square root of 25, which comes back to what? 5. When I multiply a square root by itself, it will always get rid of the square root. Because what happens is when we multiply something by itself, we've created a perfect square. That's our definition of something squared, multiplied by itself. So when we rationalize, it's not always the shortest way, but the simplest way to get rid of this square root of 2 is just to multiply it by another square root of 2. So when you multiply it by itself, it's always going to get rid of the radical. So to rationalize, I'm thinking again, no radicals in the denominator. So I'm going to multiply by something so that I get rid of this square root in the denominator. And square roots are easy. All you have to do, match it. So I'm going to multiply that square root of 2 just by another square root of 2. I'm guaranteed to get a perfect square. But question, when we're dealing with an expression, it's not an equation, we just have an expression. What's the only value I can multiply by to not change it at all? Form of 1, absolutely. So we talked about when we add subtracted, whenever we worked with expressions, we always used a form of 1. So if I multiply by something other than 1, I'm going to change the original problem, which I can't do. I need the same equivalent fraction, same equivalent value here. So if we decided that you need a square root of 2 in the denominator, you also need a square root of 2 in the numerator. This has to be a form of 1, and you can make that up of your denominator. For square root, it will guarantee to clear it. So let's multiply this across. So my numerator, 6 times the square root of 2 is just 6 square root of 2. And then the denominator is the square root of 2 times the square root of 2, which is the square root of 4. And what should always happen is this should always end up being perfect. So when I simplify, I have 6 square root of 2 over, what's the square root of 4? 2. Now just the number 2. Remember, it's perfect, loses its square root. So we've accomplished our goal of rationalizing. If I look at my denominator, there's no more radical. Can I simplify that fraction any further? What do you think? 6 square root of 2 over 2. So think about our multiplying rules. When we multiplied, two things we multiplied together. We multiplied the front numbers, and we multiplied the radicals. The multiply rules and divide rules are the same. So when I'm dividing, if I have two numbers without a square root, I can divide them. If I have two numbers with a square root, I can divide them. So I can divide the 6 by the 2, and it just gives me 3. So my final answer is 3 times the square root of 2. Now when I look at B, it doesn't look quite the same. Does not look quite the same because it's that one big radical, and you really have to read your directions here. Say a little loud, Shakira. What do you want to do? Yeah, split them up. Put them under their own radical. So the reason I recommend this as a starting point is because otherwise I find people tend to multiply the wrong things together when you don't see them as both being square roots. Now that does not answer the question at all. So the directions say to rationalize. So splitting it up has done absolutely nothing to rationalize it. It's just a setup step. So this is a setup step. Now we're actually going to do the rationalize part. And what's the goal of rationalizing? Why do we rationalize? What do we hope to accomplish? Get rid of the radical where? In the denominator. So no radical in the denominator. For square roots, that's really easy. All I do is look at my denominator and put it into a form of 1. So I have to multiply by a form of 1 so I don't change the value. And in this form of 1, we just match the denominator. So what's the square root of 6 times the square root of y? Say it again? Nope, just square root of 6y. Right. They're both square roots, so you just multiply them under a square root. And how about the square root of y times the square root of y? Not just y squared, though. Square root of y squared. And that's perfect. That should always end up being perfect. That's how we rationalize. So I have the square root of 6y, and what's the square root of y squared? Y. And then can we simplify the numerator? We've still got to look at that. If we can do anything else with the square root of 6y. Got a lot of head shakes now. That's good because there is nothing else that I can do. So we got to look at each radical still for simplifying. 6 isn't divisible by any of my perfect squares. Y has an exponent of 1. My index is 2. So we're good there. So for C, the square root of 7 over the square root of 3. What am I going to multiply by in order to rationalize this denominator? What am I going to put in my form of 1? Square root of 3. So just match your denominator. Easiest way for square roots. And that's got to be a form of 1. So numerator, square root of 7 times the square root of 3. Do I actually multiply those together or not? Yeah, they're both square roots. So we get the square root of 7 times 3 is the square root of 21. And then the square root of 3 times the square root of 3. Square root of 9, which is going to turn back into 3. And if you recognize that, you don't have to write the square root of 9. You could write just the square root of 21 over 3 there. Because whenever you multiply a square root by itself, you always get the matching radicand. So when we multiplied the square root of y times the square root of y, we got back y. Square root of 3 times the square root of 3, we get back 3. So last question, because this is where what can be hard. We got to find one we have to cut ourselves off. Can I simplify the square root of 21? No. Can I divide the square root of 21 by 3? No. So multiplying rules are the same. It's the same rules. If they both have square roots, yes, you can divide them. If they both don't have square roots, yes, you can divide them, but you don't mix the two, just like when we multiply. It's kind of the nice thing. Multiply and divide rules are the same. So go ahead and try D. Switch the page over. I want to rationalize 12 over 3 times the square root of y. All right, so what did you multiply by in order to rationalize? Square root of 3y. Square root of 3y over, make sure you put that into a form of 1. Now, in the numerator, can I actually multiply these two together, like the 12 and the 3, for example? No, one's got a square root, one doesn't, so they just sit next to each other. And then the square root of 3y times the square root of 3y. It's going to be the square root of 9y squared, which just comes right back to 3y. And right here, if they don't have a square root, you can simplify them. It doesn't matter that there's a y with the 3. This is 12 times the square root of 3y. This is 3 times y. They're all factors, so you can simplify just the numbers. It doesn't have to have a y with it. We can just simplify the 12 and the 3, which gives us 4. You still have that y left over, and it stays in the denominator. Any questions? All right, so now we're going to solve some equations that have radicals in them. It's actually, I think it's a little bit easier than some of this other stuff we've been doing because there's not going to be any simplifying radicals in it, or simplifying non-perfect radicals in it. So 10.6, it's still a topic that has to do with square roots, cube roots, that sort of thing, but just a little bit different take on it. So what we're going to be doing in 10.6 is solving radical equations, meaning these equations just have one of our square roots, cube roots, fourth roots, whatever in it. And it's kind of like fractions. When we solve equations with fractions, the first thing we do is get rid of all the fractions. When we solve an equation with a radical, the first thing we do is just get rid of the radical. So what you have to be really careful with on these problems is they do have the potential to be no solution. So we always have to check our answers. So what we're going to do, I summarized it in this little checklist here. First thing we need to do is isolate the radical, meaning on this side of the equation, there can only be one. One radical. There shouldn't be anything that's added or subtracted or multiplied that's not part of the radical. So everything's underneath here, so we're all set. Now we're going to get rid of a square root, and we're going to use its opposite operation. So what we're going to do to get rid of a square root is we're just going to match the index as an exponent. So what is my index on a square root? 2. So to get rid of a square root, all I have to do is square it. But if I'm working with an equation, I've got to keep balance. So if I square the left side, what do you think I have to do to the right side? Square it. And that's the part sometimes that gets forgotten. Make sure you keep that balance. Now, squaring and square rooting completely undo each other. If I take a square root and I multiply it by itself, I get a perfect square. We just did that with rationalizing. And I get back the radicand. So that's like when we had the square root of 3 times the square root of 3. We ended up with the square root of 9, which gave us back to 3. So whenever you have a square root, because that's really the square root of 3 squared, whenever you have a square root and you square it, you get back the radicand, just like we did with rationalizing. So when I take this square root and I square it, I get to drop both of those. I drop the square root and the squared. So I'm looking at 3x minus 2 equals, don't forget to square the right side, which is 25. And now that there's no square roots, we can solve this. So question, what type of equation are we dealing with? Linear. So I don't have an x squared, you might. But this is a nice linear equation, which means we just want to get our x's on one side, our numbers on the other. So I'm going to add 2. So I have 3x equals 27 and divide by 3. So x equals 9. But one of the things about radical equations is they can sneak in a no solution even though it looks like we can solve it. So on all of these problems, we've solved the resulting equation. We have to check our answers. So to check your answer, so we think our answer is x equals 9. To check your answer, you take the original equation, but in place of all of the x's, we're going to put our proposed solution. We want to see if that works, so we'll put the question mark. So we're not quite sure yet if that's equal. But again, it will always look like you can solve these. But sometimes the answer doesn't fit the domain of a square root. So if I work that out, I got my square root, that's going to be 27 minus 2. I want to know, does that equal 5? So I get the square root of 25. Does the square root of 25 equal 5? Yeah, so we're good. We're okay. But we will run into an example where we go to check and it doesn't work. So you'll see what that looks like. But if this works out, and this is always the principal root, unless there's a negative sign out front, always the principal root. I want to check and make sure both sides of that work out to be the same. Sometimes they don't. Now, the only ones you actually have to check, so I will tell you this, the only ones you have to check are square roots and fourth roots. Because if you have an odd index, you get a real answer for a negative underneath. So I had a lot of great answers for that in the extra credit, where I asked, how do you know if it's real or not real? If it's an odd index, you actually don't have to check. It's only the even indexes we're worried about the domain on. So B, we want to solve the radical equation. The first thing we need to do is get this cube root all by itself. So the x and the minus 5 are underneath the radical, but the 2 here is not, which means we got to kick it over. So anything underneath is fine. Don't try to pick out from underneath, but anything that's not underneath, we've got to move it to the other side. So how do I get that plus 2 over to the other side? Minus 2. So I'm looking at the cube root of x minus 5 equals negative 3. And now, what power do you think I should use to clear out a cube root? Cube, yeah. So whatever your index is, that's going to tell you what sort of exponent we need. So I'm going to take this left side and I'm going to raise it to the third power. I'm going to take the right side and raise it to the third power. Make sure you get both of them. Or we've got unbalance. Now on the left side, I have a cube root and I have a cubed. They just simply cancel each other out. You're not ever going to end up multiplying anything on your radical side. You're just going to get your radicand back. And then that equals negative 27. What type of equation do we have? Linear. So we can go ahead and solve for x just by adding 5 to both sides. So we have x equals negative 22. Now, since our original problem started with a cube root, we do not necessarily need to check this. Yeah. Right, because, so what happens is if you have this. So this is saying, pretend this was our radical, this was something else, and this was a term on the right side. This is not equal to this. So what people do is if you leave this over here, they're like, okay, I'm just going to cube this, and then I'm going to cube this, and then I'm going to cube this. That doesn't work. So what it is equal to, so it's not equal to this, it is equal to a plus b squared equals c, but then what's going to have to happen here if you have a binomial squared? You'd have to set it up and FOIL it. So it's not, you're never just squaring or cubing individual terms, it's sides. You've always got to raise the side to the power. So if you were going to cube it to start, you'd have to put this whole side in parentheses, raise it to the third power, multiply it by itself 3 times. Save yourself that work, just move the 2 over. So, because you're never raising terms to the powers, you're raising sides, whole sides. Any other questions? All right, so C, we want to solve the radical equation. Am I going to have to worry about checking my answer? Yes, why? Square root. So let's just make a note. So it's a square root. So make sure that we check our answer. So first thing we've got to do is we've got to get the radical by itself. Because again, we're not squaring terms, so we're squaring entire sides of the equation. So that plus 4 is going to throw that work off. So to move that plus 4, we'll simply subtract 4. So I have a square root of 3x plus 3 equals negative 2. So I've got the square root by itself. How do I get rid of the square root? When you're solving one of these equations, get rid of the radicals. How do I get rid of a square root? Square it. Index is 2. Match your index in an exponent, but if I square the left side, I have to square the right side. Parentheses here are important, particularly if you're using a calculator. They absolutely matter on that negative 2. So what am I going to get on the left side when I square the square root of 3x plus 3? 3x plus 3, yeah, they just take each other out. So I have 3x plus 3 equals negative 2 squared is what? 4. And if you put that in your calculator and you get negative 4, it's because you did not use parentheses. What type of equation is this? Linear. Hold them tight there. So I can subtract the 3. So I have 3x equals 1. Divide both sides by 3. And get x equals 1/3. Now don't be discouraged by fractional answers. They are not bad to check. So we said we have to check it. It's a square root. But when we go to check it, let's go back to our original problem. So I'm starting with the completely original setup. Oop, there's no x. I'm going to replace the x with my proposed answer of 1/3. But everything else around it's going to stay the same. So plus 3, a plus 4 outside. I want to know, does that equal 2? So does everybody understand when I set up my check? I'm just taking my answer, going back to the original problem, and putting it in place of the x. Well, I see if this works out. And we put it's a real math thing to put the question mark over the equal sign because we're not sure. So I said the fraction's not bad. What's 3 times 1/3? 1, yeah. So if you set this up, you can put this over 1. You get 3 over 3, which is 1. So even though it looks bad because it's a fraction, it turns into 1. So 1 plus 3 is under the square root. The plus 4 is outside. I want to know, does that equal 2? So I have the square root of 4 plus 4 on the left side. And the square root of 4 is 2. So 2 plus 4, I want to know, does that equal 2? Doesn't work. I get 6 is equal to 2. I didn't get the same thing on both sides. So even though it looked like we got a solution here, this problem is actually, so we can't have the 3. We just have to write no solution. And the reason being, we can't take the square root of something, if you go back to this step, and have it equal to a negative value. So the square root of any number is not going to be negative. That's why that happens. So if you check and it doesn't work, you don't get the same value unless you've done something wrong. That's the other possibility. So you did something wrong, but we're going to say no solution. All right, D. Do I have my square root all by itself? That's the only thing on the left side. And how do I get rid of a square root? Square it. Now, we go ahead and we say, okay, so this is 2x plus 1. I'm going to square that. As I mentioned before, we don't just square terms. We square entire sides. So when I go to the right side, I put the whole thing in parentheses, and I square it. So just like we put the left side in parentheses and square it, we put the right side in parentheses and square it. So on the left side, what am I going to get? Square root of 2x plus 1 squared. 2x plus 1. That one's easy, because I got those two things that cancel each other. On the right side, though, I heard a couple different things. What did you say, Christy? Okay, what did you say, Napoleon? Yeah, so we've got to go back to that second day of class. Write that twice so we can FOIL it. So we're going to get x squared minus 7x minus 7x plus 49, which is, so we're going to have x squared minus 14x plus 40. What type of equation is it? Yeah, this one's quadratic, so this one's got some more work. Now we got to go back to Unit 1, we got to go back to Chapter 6. And actually, when we get to Unit 4, it'll be so much nicer, though, because we'll have so many different methods for solving quadratics. We don't have to rely on factoring. All right, if I'm going to solve an quadratic equation, first thing I got to do, what do you say, Tiffany? Set it equal to 0. Okay, do I want to take everything to the left or everything to the right? Everything to the right. I want it to the right. Yeah, I got that 1x squared. It means when I get to my factoring, I'm golden. So I'm going to take that 2x and that plus 1 over. So I'm going to do a minus 2x and a minus 1. Minus 2x minus 1. So I'm looking at 0 equals x squared minus 16x plus 48. All right, so now that I've got it equal to 0, if I'm solving a quadratic, what's my next step? Factor. So I'm looking for the pair that multiplies to 48, adds to negative 16. And 12. Both have to be negative, so they add to a negative but multiply to a positive. And then what do I do with each factor? And you put each of those factors equal to 0. Stuff doesn't go away in this class. It just keeps popping back up. So I'm going to have two answers, potentially. Positive 4 and positive 12. Do I have to check this one? Do I have to check in this problem? Yes. Why do I have to check? Square root. So we're going to check it because it's a square root. Again, cube roots you can get away with not checking. Square roots, fourth roots, you'd have to check. Now, I'm going to actually have two different checks. I need one check for x equals 4 and a separate check for x equals 12. So for x equals 4, let's go back to our original. In place of our x's, we can get our 4s. I want to know, does that equal 4 minus 7? Put my 4 in. So I had to substitute two places, both with the 4 to start. So I'm looking at the square root. Let's see, 2 times 4 is 8 plus 1, so the square root of 9, I want to know, does that equal negative 3? What's the square root of 9? 3. Is 3 the same as negative 3? No. So we know we've got to at least toss out the 4. We've got to toss out that 4. Again, when you're looking at the square root of 9, it's principal root only. So sometimes you overthink it. You say, well, we talked about before, we can have that principal and negative root. Square root of 9, 3, doesn't work. So we've got to separately check the 12. Let's see if we can get anything to work, make all this worth something. So I want to know, are these two things equal when I replace both the x's with the same number, both with 12? So the square root of 25, so I have 24 plus 1 is 25. I want to know, does that equal 12 minus 7 is 5? Yes. Yeah, okay, so good. Whew. Hate to do all that work and have no solution again. So the quadratic gave us 2 answers, but only one of them fit the domain for square roots. So the only answer that we'd write in the end is just that x equals 12. The 4 doesn't fit into this problem. Questions? Now the last one looks maybe the worst because it's got more than one radical in it. Now if you have more than one, you keep them on opposite sides. The only time this would get really messy is if then they like had something added after the radical, then you'd have to put it in parentheses and like FOIL it, and I would just get to nonsense really fast. How do I get rid of a square root? Square it. If I square the left side, what do I have to do to the right side? Square it. So the square root of 6x plus 2 squared is 6x plus 2. So squaring that left side just canceled those out. I have 6x plus 2. On the right side, this time I have a square root and a squared again. What's going to happen with the square root and the squared? You're going to cancel out. So all that's left, 5x plus 3. It's just the radicands have to be equal. If you have two radicals equal, their radicands have to be equal. What type of equation is this? Linear? So I don't have the x squared. I have two things that have x's in them. That doesn't matter. It's still linear because none of them are raised to the second power. So just x's to one side, numbers to the other. I'm going to subtract the 5x, so I get x plus 2 equals 3. Subtract the 2. So I get x equals 1. Do I have to run a check on that, or am I good? I gotta check square roots. Stupid square roots. Gotta check it, square roots. So in both sides, in place of the x, we're going to substitute our 1. And we're going to see if these work out to be the same. So on the left side, I have 6 times 1 plus 2. It's all under the square root, so it's the square root of 8. On the right side, 5 times 1 is 5, plus 3 is 8. It's all under the square root, so the square root of 8. Are they equal? Yeah, that's all we care about. I don't have to simplify them. All I care is that I can say, yes, this side is the same as this side. It's okay that they're not perfect. They're the same. As long as the two sides are the same, we know our answer checks. Questions?